This is a video for AQA Further Pure Mathematics, Numerical Methods section 1.1, which is looking at the idea of numerical integration using the Midordinate rule. Well, numerical integration is the idea of finding approximate values to definite integrals, i.e. the area under a curve between 2 points, based on usually subdividing the interval into subsections and then approximating the value of the function on each of those sections in some way. And one way of doing the approximation is to use rectangles, and that's the idea we're going to look at in this particular video. Well, to illustrate the method, I'm going to look at the integral of 1 over x from 1 up until 2. Now, of course, this is an integral that we can't evaluate exactly, so this is the curve that we're looking at, and the integral of 1 over x will be natural log of x. So if you evaluate that between 1 and 2, we'll see that the answer is 0.693 to 3 decimal places. That will just give us a comparison as to how well the approximation is achieving its desired result. The approximation I want to first of all look at is the idea of using a rectangle, just a single rectangle. Obviously not a very good approximation, but I'm going to evaluate the height of the rectangle by looking at the point which is halfway between the endpoints of the interval, in other words at 1.5. Now obviously that height will be 1 over x, which is 1 over 1.5, so that the size of the approximation, we can say that that's approximately equal to the 1 over 1.15, which is the height of the rectangle, and then multiplied by the width of the interval 1. And that gives us a value of 0.6 recurring, or to 3 decimal places 0.667. So you can see that it's not too far out, but certainly it's an underestimate of the actual value of the integral. So then we consider, well, how can we improve this? Well, the obvious answer is to use, instead of one interval, to use 2 intervals. So here's the situation we get if we use 2 intervals, where now the midpoints of each of the intervals, or the subintervals, is at 1.25 and 1.75. And therefore the area that we have is equal to 1 over 1.25 plus 1 over 1.75 multiplied by the width of each of these intervals, which now, instead of being 1, is now 0.5. And if you evaluate that, we get a value of 0.686. So still an underestimate of our actual integral, but much closer than the first one. We can make a further improvement by taking this time 3 rectangles. So you can see therefore that each of these points now is going to be 1 plus 1/6 here. So this is at 7 over 6. The next one will be at 9 over 6. And finally 11 over 6. The area will be equal to 1 over each of those, 1 over 7 over 6 plus 1 over 9 over 6 plus 1 over 11 over 6, and multiplied by the width of the intervals, which of course now the total interval is 1, so this must be 1/3. So easier now to work in fractions. But if we calculate that as a decimal to 3 decimal places, it becomes 0.690. So you can see that again an improvement on the approximation becoming closer to the actual value of the integral, which was 0.693. So as we increase the number of subdivisions or subintervals that we're using, then the value of the integral gets better and better. The midordinate rule then refers to the fact that we're using the midpoint of the intervals or the subintervals that we're using here, which are referred to in the formula as y1/2, y3/2, etc., up to the last one, which will be at y is n minus a half, if we're dividing our interval from a to b in n strips. So if we have n strips, then the width of the interval, which is referred to here as h, will be b minus a, that's the width of the whole interval, b minus a, divided by the number of strips, which is n. So h is b minus a over n, and then the midordinate rule says that the integral will be approximately equal to h multiplied by, and then in a bracket, each of the values of the function, so the y values at these midordinate points, the y1/2, y3/2, etc. And we've seen in our examples that as the number of strips increases, the accuracy of the approximation increases. We saw that in the particular example that we did, that the approximation was an underestimate. And in the next video we'll look at when that happens. When do we get an underestimate, or is it possible for the midordinate rule to overestimate the value of an integral?